In our previous lecture, we introduced transformation and looked at classes of transformation as a nested groups. In today's lecture, we will continue with the affine transformation and look into the combination of different transformations together. We will also see rotation transformation in depth. We have already seen how rotation can be done through around different axes, x-axis, y-axis and z-axis. If we would like to rotate around an arbitrary axis, then how do I treat these problems? Representing and combining transformation. We've already seen Introduction to Transformation. We have also studied the classes of transformation as a nested group. Now we will look into the representation of transformation. We have seen that for a normal transformation in two dimension, x prime can be written as ax plus by plus c, and y prime is equal to dx plus ey plus f. This transformation can be written in a matrix format where I have x prime y prime being a vector is equal to a matrix A, B, D, E multiplied by the vector x, y plus a translational vector CF. P prime is equal to MP plus T is the equation. In affine transformation, we have seen that we could enlarge the matrix by 1, that is, increase the dimension of the system by 1. So this is a two-dimensional system, it becomes a three-dimensional system. And in that case, I just have a simple matrix multiplication where x prime, y prime, omega prime is equal to the matrix A, B, C, D, E, F, 0, 0, 1 multiplied by the vector x, y, omega. And as we see, the translational components come in the last column as C and F followed by a 1 which keeps the value of omega same. And in an equation format, it becomes P prime is equal to M subscript A is affine transformation in 2D. So we call these coordinate as homogeneous coordinate. What we do is we add an extra dimension to it. In 2D we use a 3 by 3 matrices, and in 3D we use a 4 by 4 matrices. Each point has extra values of omega that is given here, and you can write it in this general form in 4 dimension as P prime equals to MP. Most of the time W is equal to 1 and we can ignore it. If we multiply a homogeneous coordinate by an affine matrix, W is unchanged. Homogeneous visualization. If W is not equal to 1, we divide by W to normalize or homogenize. In case where W is equal to 0, we say the point is at infinity direction. Here I have a set of points. Say for instance, I have a point in 2 dimension which is the origin, which is given as 0, 0, 1, which could be also equal to 0, 0, 2, 0, 0, 3, and so on and so forth. All these are possible coordinate systems in the higher dimension with W. but we will consider the only dimension which is with w equal to 1 as the real world. The other worlds are sort of a pseudo world and needs to be normalized to get to the real world. So the 7 comma 1 comma 1 could also be represented as 14 comma 2 comma 2, but the real world would be represented by 7 comma 1 comma 1, where w is normalized or w is equal to 1. Similarly, 4 comma 5 comma 1 is the real domain, while 8 comma 10 comma 2 is a pseudo world or an extension of the real world. Homogeneous coordinates: add an extra coordinate w to a point. So if I have a point P of x, y, we add an additional coordinate w. To set of homogeneous coordinate representation represent the same point if they are a multiple of each other, that is 2 comma 5 comma 3 and 4 comma 10 comma 6 actually represent the same point, as we see they are multiples of the same point. So dividing the first coordinate by 3 and the second coordinate by 6, we will get the real world which is connected with these similar points. The condition is at least one component must be non-zero and 0, 0, 0 is not defined. If w is different than 0, we divide it to get the Cartesian coordinate of the point, or which I call the real world. That is, I divide x by w, y by w, and w by w, so it always becomes 1. If w is equal to 0, the point is said to be at infinity. If w represents x comma y comma w in 3D space, all triples representing the same point describe a line passing through the origin. If we homogenize the point, we get a point of the form x comma y comma 1. Homogenize points from a plane at w is equal to 1. The figure shows that any point P, you could connect it with the origin, and wherever this point P cuts the plane w is equal to 1 is the Cartesian coordinate or the real coordinate of that specific point. Here is an enlarged picture of the same figure, where you see the point P is connected to the origin of the coordinates. Here you see it's a two-dimensional plane, that is x and y, while w being the vertical vector, and the blue colored plane is the w is equal to 1 plane, and you have the point P which is connected to the origin and connects to the point, this point, where this point is on the plane w is equal to 1. So we have seen different simple transformations like identity transformation, translation, rotation, isotropic uniform scaling. We have seen anisotropic scaling. We have also seen reflections, and finally the shear transformation. The classes of transformations have been derived from it, and these classes are nested groups. We need to define affine transformation, which is actually combining linear transformation and similitude groups. And over the affine transformation is the projective transformation, which we will visit in a later lecture. This is important to understand that processes or some of these transformations are non-commutative. As all matrices, multiplication of all matrices are not commutative, similarly here, all transformations are not commutative. Here the question asked is, why bother with an extra dimension? The answer is because translation can be encoded in the matrix, or translation which was nonlinear has been linearized by adding an additional dimension to the problem. Scaling. Isotropic scaling, I have got Sx has to be equal to Sy, which has to be equal to Sz. The transformation matrix is basically a diagonal matrix where I have got the diagonal elements Sx, Sy, and Sz, and the column and the row for W is equal to 1, and other elements are 0. This is a scaling transformation. Homogeneous form of rotation transformation. In two-dimensional, I could write this as cos theta minus sine theta cos theta, and I have got 0, 0, 1 and in the column, and of course that is the omega coordinate. And we have already seen that rotation, the inverse rotation, that is R inverse is equal to R of minus theta. The rotation matrices are orthogonal, and which means that R inverse theta is equal to R transpose theta. We have seen that the sign of sine theta changes while the sign of cos theta does not change, as theta becomes a negative quantity. So I have a rotation about the z-axis in the four-dimensional coordinate system, which is given here, and this could be written in short as P prime is equal to Rz theta times P. R subscript Z means that the rotation has taken place around the z-axis, and theta being the angle of rotation around the z-axis. Similarly, I have a rotation about the x-axis and y-axis. Please note again, for the y-axis, this change of sign. Now, these transformation also can be written in a short form as P prime is equal to Rx theta P. This is for rotation around x-axis, and for rotation around y-axis, P prime could be equal to Ry of theta times P. Now, supposing if I have a rotation around an arbitrary axis k, let us draw the axis. We have the three-dimensional coordinates x, y, and z. And if I draw an arbitrary vector k, and let us see if I would like to rotate a point P around this vector k, that is the rotation plane is perpendicular to the vector k. So p rotated by theta will move to a coordinate p theta superscript theta, x superscript theta, y superscript theta, and z superscript theta. This equation in general could be written as p superscript theta of x superscript theta comma y superscript theta comma z superscript theta is equal to r k of theta times pxyz. Now we do not know how to do a rotation around an arbitrary axis k, but we know how to rotate around x-axis, y-axis, and z-axis, which can be seen here where we have rotated around x and y-axis, and here we have rotated around the z-axis. Now let us write the vector k in dependent on its three components, that is kx, ky, and kz. The vector k makes an angle beta with the y-axis. The projection of vector k on the xz plane makes an angle alpha with the x-axis. Now let us do a series of transformations, but before we do the transformation, let us see the vector k and its contribution to each of these axes. That is, the projection of k on y-axis is ky, the projection of k on x-axis is xk, and the projection on the z-axis is kz. These, if the angle between k and ky is beta, and the angle between the projection of k on the xz plane with x-axis is alpha, then you could write the values of kx, ky, kz in this format, where ky is equal to k cos beta, x is equal to k sin beta cos alpha, kz is equal to k sin beta sin alpha. What we are going to do is that we try and align the yx plane over the vector k so that k becomes part of this plane. So what we do is that we apply a rotational transformation around y-axis by an angle minus alpha. And if I do that, I get my new coordinate x prime and z prime, and by rotating around this coordinate system, my new under the new coordinate system, my p will have the coordinate, that is p prime will be p prime of x prime, y prime, z prime will be equal to rotation around y by an angle minus alpha of point pxyz. Please note that the vector k is on the xy plane. The xy plane has rotated, and of course this is an x prime y plane, and this plane is aligned with the k vector, and the k vector exists on this plane. If I want to return to my original coordinate point, that is px, py, pz, we could easily apply the inverse transformation being ry of alpha. When the rotational transformation was ry of minus alpha, the inverse is ry alpha. Please note the the latter portion Ry of minus alpha p x y z is equal to the transformation for obtaining p prime of x prime, y prime and z prime. Z prime is perpendicular to this plane x prime y. I could rotate the coordinate system around this plane such that the vector y now is superimposed on vector k. Since vector k is part of the plane, I could superpose the y vector on the k vector by doing a rotation around z. So if I do this rotation around z, the amount of rotation angle is beta or minus beta. So p double prime, x prime, x double prime, y double prime, z double prime is equal to rz prime of minus beta, p prime, x prime, y prime and z prime. P prime can be written as a function of p, that is ry minus alpha p x comma y comma z. So what we have is two rotational matrix, but these two rotational matrix are not along the same axis. So if we write this equation down and again come back to the original coordinate, so I need to do an inverse transformation also. The inverse transformation being rz beta and ry alpha. So I get this equation here. Please note that the second half or the latter portion of this equation is equal to the p prime point which is there. Now what you see is that at this point, that is between these two transformations, the region is at that region that you see here, the region here in the middle where I have created a gap. The vector k is along the y-axis. So if I apply this rotation by theta at this location, that is the vector k is along the y-axis, so the rotation axis will be a rotation around the y-axis, and if I do that, I will be able to rotate the point P into P theta, X theta, Y theta and Z theta. So this is possible by rotating at this position and the rotation being Ry of theta, and the final result changes to P theta, P superscript theta, theta x, comma theta y, comma theta z. So this is a sandwich jugglery where I'm sandwiching a set of two rotation on either side, the inverse rotations on the other side, and in the process I'm enabling the device to rotate around an arbitrary axis, that is the axis k, which we could write it as a set of two rotational transformation, then a rotational transformation around with theta, and then again doing an inverse transformation to bring it to the initial coordinate system. So here I have, about rotation about kx, ky, kz, a unit vector on arbitrary axis. It's the Rodriguez formula with the formulation that has been given in previously, that is the formulation given below. One could easily calculate the rotation transformation around an arbitrary axis. This rotation can easily be seen. It's a complex function, but if one knows how to derive it, one could always derive this function for specific problems. So here please note that the angle cos theta is defined as C and sin theta is defined as S. So this was representation of transformation. So let us see how do I combine transformation. All combinations are not reversible, that is not commutative. Here I have a transformation where I am scaling and translating. So I have a cube which is of 1 comma 1 which I scale it by 2, so I get the cube as 2 comma 2, and then I apply a translation. Then the cube which was connected with the origin is moved to a point 3 comma 1. Please note that the transformations are non-commutative. So what you have here is I am doing a scaling by 2 and a translation by 3 comma 1. Now if I do a translation of 3 comma 1 and then do a scaling of 2 comma 2, what I see is the translated amount, that is 3 comma 1, gets also scaled to 6 comma 2, and the cube is 8 comma 4. But what you see here, the cube has shifted from the origin. Concatenation, we perform two translation on one same point p prime, which is p times the translational matrix. P double prime is p times the translational matrix with a different translation, that is dx2 and dy2. So when I combine both the cases, here I'm applying both the translation. Here you see the translations add up, and so it doesn't matter if I translate first to p double prime or then translate to p prime, the effect is the same. Here what we see is that the transformation is symmetric, or you can say that the transformation in this case, when I do a two translation, that the translation is commutative. The matrix product dtx1 and dy1 multiplied by t dx2 comma dy2 can be written here. The matrix product is a various referred to as a compounding concatenation of composition. So these are the few properties of translation, and we can note that translation matrix are commutative. The order of application does not matter. Now let us recall scaling. Scaling is given by this in 2D as well as in 2D homogeneous coordinates. So this is the solution that we get. Only the diagonal elements of the matrix there, it's easy to multiply, and in such cases I see that it is commutative. These are other cases where similar effects are seen. So if I rotate around the same axis by an angle theta and then rotate around the same axis by an angle phi, I could swap their position, first do a rotation around phi and then a rotation around theta, and this is valid. But if the rotation axis changes, it is no more valid, and you have to be careful in maintaining the sign bit. Before we end this video lecture, let me give you an assignment. What I would like you to do is try and see if you can generate this structure Here are some more examples where a repetition of transformations have produced a beautiful leaf or some effects which can easily be seen. We will see these effects when we study fractals.